Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Ministry of Aeronautical Engineering, Hyderabad. Today we are discussing the problems which are related to critical thickness or the critical radius in heat and mass transfer circuit. Here in daily life, in order to reserve the energy or conserve the energy, generally the objects are insulated. The thermal insulation of material should have low thermal conductivity. It will not allow the flow of heat energy from the fluid, that is from inside to outside, or it acts as a barrier to prevent the flow of energy from higher temperature to lower temperature. The insulating property of the materials depends upon the transfer property of the gases filling void spaces, particularly in the case of solids. The adding that insulation materials to a container or the barrier generally decreases the conduction resistance, or it decreases the flow of energy or increase the conduction resistance. When the total resistance, particularly in the case of cylinders having negligible thickness, as in T1 is representing the temperature the fluid contains inside it, and the outer surface is insulated to prevent the flow of heat energy from inside to outside. Here, the heat transfer, here we are decreasing the flow of energy, but totally it cannot be minimized. So the total heat energy that is flowing from the inside of the container to outside container, it consists of two processes. One is conduction process, one more is the convection process. Here from inside cylinder, that is the hot gases, to the surface, the convection process is taking place, and from walls of the cylinder, the conduction process taking place. Afterwards, again convection process taking place to dissipate to environment or outside of the fluid. That is the total conduction process, that is total the energy flowing from inside to outside. It consists of two processes, or the combination of two processes. One is the conduction, another one is the convection. Here, because of insulation process, the conduction resistance increases, hence the flow of heat energy that is decreases. But in the case of convection process, the surface area of outside insulation, because of 2 pi R2 into L pi d into thickness, hence that is increases. Hence the heat transfer by using convection process is increases. Or in another words, the convection resistance of the insulation material, when it is added, it is decreases, hence the flow rate is increases. Here, according to the convection process, the heat energy is equal to, we can take it as Q is equal to HEA into T1 minus T2 now. It is a general expressions where T1 and T2 are the temperature differences. Assume T1 is the temperature of the hot fluid, T2 is the temperature of the surface in contact with that fluid. The heat energy is flowing by using convection process given by Q is equal to HE into T1 minus T2. Here, because of decreasing convection resistance, the heat energy that is flowing, it is gradually increases at certain values. After that, it decreases. That is the resistance, that is the thickness of the insulations or the radius of the outer surface at which it is having maximum flow of heat energy. That radius is known as a critical radius in terms of spheres as well as the cylinder, but for the walls it is known as a critical thickness. The main application of the critical radius is used in electric transmission cables. Generally, when the heat current is passing through the cables, the temperature of the cables increases. In order to dissipate the heat energy from that cables, it is insulated with the materials such that the thickness is equal to the critical thickness at which the maximum amount of heat energy that is dissipated from it now, so that the temperature of the cable becomes lower. So here we have to determine the critical radius of insulation. Here now we are taking a cylinder having internal radius is equal to R1, carrying a fluid which is at a temperature T1 as shown in figure. So from the hot fluid to the this walls of the container, that heat energy flows by using convection process. The outer surface of the cylinder, it is insulated to a thickness of T such that which is equal to the radius of the difference of radius of R2 minus R1, where R2 is representing the outer radius of the pipe when it is insulated. R1 is representing the radius of the inner surface now. So the difference of R2 minus R1 is representing the thickness of the insulations. From R2 to again R1 to R2, the heat energy flows by using thermal conductivity. Just from R2 to outer surface, the heat energy flows by using convection process. That means the heat energy flows from the fluid which is inside the cylinder to the cylinder surface by using convections. From within the cylinder walls, conduction process. From outside of the walls, it is a convection process. That is here three types of, that is convections, conductions, as well as the convection process that are taking place to flow of heat energy from the inside to outside of the cylinder. So the heat transfer rate per unit length from the cylinder is expressed just by using the equations now. T1 minus T alpha, where T1 is representing the temperature of the hot fluid, T alpha is representing the temperature of the outside fluid of the cylinder. Generally here we are taking atmospheric air now. That is the T1 minus T alpha divided by, here it is equal to 1 by 2 pi R1 L into H1. Here this is representing the convection resistance offered when the heat energy is flowing from the fluid to the surface of the inner wall of the cylinder. Plus 1 by 2 pi K into L log A R2 divided by R1. This is the conduction resistance for the circular plate now, where R2 is representing the outer radius, R1 is representing the inner radius of the cylinder. Plus 1 by 2 pi R2 L 1 by H02. This is known as air convection resistance now. So in order to flow maximum energy from the fluid which is from inside of the cylinder to outside, the resistance should be minimally required. So this is obtained by differentiating this equation number 2 with respect to the R2. So here now the total thermal resistance for this arrangement is the sum of the inside convective thermal resistance, conductive thermal resistance, and outside convective thermal resistance. Hence, in order to get critical thickness, that is the outer radius of the cylinder. So that is at which the heat energy which is flowing, it is the maximum, it is obtained by differentiating equation number 2 with respect to the R2 now. So I am doing this differentiation with respect to the R2 now. Since in the first equations 2 pi 1 by 2 pi R1 1 by H1, this is known as here first one is convective resistance, but this value depends only on inner radius of the cylinder. Hence, this is treated as the constant values. The second one term, the conduction resistance is equal to 1 by 2 pi K. into log A, R2 by R1. Here, this is known as the conductive resistance. It depends upon the values of R2 as well as R1. Since R1 is a constant, that is the conductive resistance it increases with the increasing value of R2. Here the third term is there now. A convective resistance for flowing heat energy from the outer surface of the cylinder to the air is here now convective resistance. But these values depends upon the R2 values. When the R2 values increases, that is the resistance decreases, hence heat energy flows, that is values increases now. So it should be in order to get the insulations, that is the thickness of the insulation or the outer radius R2, just in order to get at which we are having just maximum heat flow energy obtained. Already we did by using this differentiation, again it is equal to 0. And solving these equations, since R1 is a constant, first term is equal to 0. From this one, we got common term when we are taken 1 by 2 pi R2. Here in this case, the first one 1 by 2 pi k is there now. Log A R2 by R1. So the differentiation is equal to 1 by R2 minus of 1 by 2 pi H0 is the constant now. Again 1 by R2 differentiation is minus of 1 by 2 R2 square now. Okay, it is given here now. So again it is equal to 0. The term is there 1 by 2 pi k is a constant for this one R2 divided by 1 by k minus 1 by R2 H0 is equal to 0. So in this case, in order to get R2 is equal to 0, equity equal to 0, the term 1 by 2 pi R2 is equal to 0. That means nothing but R2 is equal to 0 required now. The second one is, since it is not possible now, because it is having internal radius as well as the outer radius, this equation not applicable. The second one is 1 by k minus 1 by R2 H2 should be equal to 0. From this relations, R2 is equal to k by H0 is known as a critical radius, that is the radius, outer radius at which the maximum amount of energy that flows now. So from these relations, we can determine the thickness of the insulation, which is the difference of outer radius to inner radius. So which is equal to k by H0, where k is representing the thermal conductivity of the materials, H0 is representing the convective heat transfer coefficient for the insulating materials. Okay, based on these equations, we are taking one problem now. A copper pipe carrying refrigerant at minus 20 degrees centigrade is 10 mm in outer diameter and exposed to convection at 50 watts per meter square per degree Kelvin to air at 25 degree centigrade. It is proposed to apply insulation of conductivity 0.5 watts per meter per degree Kelvin. Determine the thickness behind which it will gain will be reduced now. So calculate the heat gain for 2.5 meters, 2.5 mm, 5 mm and 75 mm thickness for 1 meter length. So the critical thickness of the insulation is equal to at which the maximum amount of heat energy flows through the pipe is obtained by using the relations RC is equal to K by H, where K is the thermal conductivity of the copper, H is equal to here now, that is insulation. According to the problems is given 0.5 is the, here is given thermal conductivity of the, here given, divided by, here H is equal to convective coefficient resistance, which is equal to 0.5 divided by 50. From this relationship we got it is equal to 0.01 meters. Okay, we completed up to this one now. Okay, from this relationship we got the thickness of the materials is equal to insulation is equal to, because the 10 mm is representing the that is critical radius now, that is 0.01 here meter, which is equal to 10 mm is given now. So here the thickness of the critical insulation is equal to, which is equal to R2 minus R1, which is equal to here 10 minus here 5, it is equal to 5 mm. 5 mm is representing the thickness of the insulation that required, it which maximum amount of energy that flows. The heat energy flows at various configurations given. For the bare pipe, that is when it is not at all insulated, we are having the equations Q is equal to HA into delta T, because the thermal conductivity is having this very negligible thickness. We can take directly is equal to HA into delta T, which is equal to here H is equal to 50 into A is equal to 2 pi r into length, the surface area, which is equal to 2 pi into 0.05 into here the difference of temperature. The temperature inside here is given, the solutions 25 minus 20, which is equal to 70.69 watts per meter. This is the amount of heat energy that flows from 20 degrees centigrade to minus 20 degrees centigrade when it is not insulated. Now just we are adding insulations and measuring what is the amount of heat energy that flows at various thicknesses. Now, when we are having this thickness is equal to 2.5 mm thickness, that means we are having this T is equal to R2 minus R1. From this relation, so R2 is equal to here R1 plus T now. That is when thickness is equal to 2.5 mm thickness means R2 is equal to 5 plus 2.5, which is equal to here 7 mm. That at 7 mm, the amount of heat energy that flows is given by here Q is equal to 145 divided by here it is due to the conductivity 1 by 50 into 2 pi into 0.0075 into length plus here is given log in 0.0075 divided by 0.005 divided by 2 pi into 0.5. From this relationship we got which is equal to 81.3 watts per meter is given now. So because of adding insulation from this one now, without bare it is a 70.69 is there. Because of presence of insulation, so it is increases 81.3 now. It is only because of increasing in the surface area of the cylinder, the convection process, that is the heat energy by using convection process is increases. So when we are taking again 5 mm thickness now, the 5 mm thickness is equal to R2 is equal to, by using the same relation, so R2 minus R1. From this relation we got here R2 is equal to T plus R1, which is equal to here 5 mm thickness plus 5 mm the radius. From this relationship we got it is equal to here 10 mm radius now. So on substituting here now Q is equal to again now 45 divided by 1 by 50 into 2 pi. This is nothing but here A plus log of is given 0.010 divided by 0.05 divided by 2 pi into 0.5. By using this calculation, we got 83.49 watts per meter. That is because of addition of this insulation up to 5. Again, the rate of heat energy flows increases up to 83.49. But at a 7.5 mm thickness, that is R2 is equal to 5 plus 7.5, which is equal to 12.5. It is behind the critical thickness now. So by substituting these values in this equation, Q is equal to 45 divided by 50 into 2 pi into 2 pi r into 1 is required. The radius is equal to 0.0125. That is increases into 1 plus this value we are taken log of 0.0125 divided by 0.05 divided by 2.05. From this relationship we got it is equal to 82.37. That is this value is increases. That is the amount of heat energy flows because of addition of insulation materials up to the thickness is equal to this 5 mm. That is a critical radius. So we are taken 10 mm up to 10 mm. This is behind 10 mm. That is and adding this like here example we are taken 7.5 mm thickness. the amount of heat energy that is decreases. So the radius at which the maximum amount of energy that flows is known as the critical radius of the cylinder. Okay, one more second problem. It is a desire to increase the heat dissipated over the surface of an electrical device of spherical shape of 5 mm radius exposed to convection with H is equal to 10 watts per meter square per degree Kelvin by encasing it in a transient spherical sheet of conductivity 0.05 watts per meter Kelvin. Determine the diameter of the sheet for maximum heat flow for a temperature drop of 120 degrees centigrade from the device surface. Determine the heat flow for bare and sheeted device. So the given problems, the given data is here. The radius of the sphere is equal to, here 5 mm is given. Convection coefficient is equal to 10 watts per meter square per degree Kelvin. And conductivity of insulation is equal to 0.04 watts per meter per Kelvin. Change in temperature is equal to, is given 120 degree centigrade now. Let the diameter of the sheet for the maximum heat flow be d now. That means this is when the maximum heat energy flowing, the outer radius is treated as the radius, critical radius. So generally it is represented RC here now. RC is equal to here now d by 2 now, where d is the just diameter of the pipe just when insulation material is added. For critical radius of the sphere now, it is equal to 2K by H. This is the formula is there now. For the cylinder, it is equal to K by H. For the sphere, it is a double twice 2 into K by H. From this relationship, we got 0.5 by 50. That is 2K by H into. From this relation, we got it is equal to 0.008 or it is equal to 8 mm. So the diameter is equal to now 16 mm now. For the bare device, when the insulated material is not added, the amount of heat energy that flows is given by P is equal to 4 pi R1 square H into delta T. Here, this is known as the surface area, 4 pi R square by H, the total area multiplied by delta T. Delta T is nothing but representing a change in temperature. 4 pi R square surface area multiplied by heat transfer coefficient H multiplied by change in temperature. From this relation, we got to 0.377 watts. When it is sheeted is there now, that is the conductive material when we are taking. Q is equal to minus of Ka dt by dr. Here, from this relationship, we got to here now K into 4 pi R square T1 minus T2 divided by 1 by R2 minus R1 into 1 by R2, which is equal to 4 pi K into T1 minus T2 divided by 1 by R1 minus R2 now. The substituting values of T1, T2, R1, R2 in these equations, we got amount of heat energy flows when the device is having sheet materials, which is equal to 120 divided by 1 by here given 1 by 4 pi K is given 0.08 whole square into 10. Here the plus is given 1 by 4 pi into 0.04 divided by here 1 by 0.05 minus 1 by 0.008 now. And substituting these values we got to, it is equal to 0.439 watts, approximately here 16% of heat energy flow that increases because of addition of insulating materials. Here mean area concept. Okay, this is the important term generally used in calculation of heat energy flows from the pipes when it is insulated. When the area changes in the direction of the flow, that is because of insulation pattern, sometimes it is convenient to use the mean area and heat equations applicable, particularly here to slab. That is Q is equal to Here the heat energy that flows by using conduction process is equal to Q is equal to T1 minus T2 divided by L by K here now. This concept is applied to the cylinder, which is equal to Q is equal to T1 minus T2 into K into AM, here mean area divided by L now. Or it is equal to T1 minus T2 is there 2 pi L into K log of R2 by R1. So AM is equal to, now mean area is equal to, from this relation we got 2 pi L into R2 minus R1 log of R2 by R1. R is equal to 2 pi L into R2 is equal to the surface area A2 divided by A1, which is here, and multiplying, just dividing by 2 pi, here we got log of A2 divided by A1. That is R2 divided by R1 is equal to, here we are taken A2 by A1, where L is equal to N we are given now, R2 minus R1. Similarly for the sphere, that is the mean effective area is equal to 4 pi into under root of R1 and R2, where R1 and R2 is representing the internal as well as the external radius of the sphere. Okay, based on mean effective mean area, we are having one problem. A hollow cylinder of inner radius is equal to 0.16 mm and the thickness is 8 centimeters, conducts heat radially. Determine the mean area and check for heat flow. The given that the problem is the inner radius of the hollow cylinder is given 0.16 meters. Thickness is given, that is 8 centimeters, which is equal to 0.08 meters. The outer radius is equal to R2 is equal to, we can take it as inner radius plus thickness. From this relationship we got 0.16 plus 0.08 equal to 0.24 meters. So mean area is equal to AM is equal to A2 minus A1 divided by log of A2 by A1, and substitute the values of A2 and A1, that is it is equal to 2 pi R into L, that is surface area when we are taking 2 pi and L is the common, and the remaining term is 2 pi into L of 0.24 minus of 0.16, that is the external radius minus the internal radius divided by log of here A2 required 2 pi into L into 0.24 divided by 2 pi into here 0.16 into L now. Considering as a slab now, the mean area of thickness R2 minus R1 and conductivity K is given by using this relation. Here we can determine the amount of heat energy that flows is given by K into 2 pi into, here mean area is equal to 2 pi into 0.24 minus 0.16 L divided by log of 2 pi 0.24 into L divided by 2 pi into 0.16 into L. This is known as a mean area. That is K into E now. That is Q is equal to, we are having formula A now, K into A into, it is given, and T1 minus T2, that is known as the temperature gradient required. So into K into delta T divided by 0.24 minus 0.16, this is known as here now change, that is the thickness of the insulation divided by here L. From this relation, so here we are assuming it is applicable for the mean area of AM as well as the thermal conductivity K. L is equal to length of the pipe. From this relationship we got 2 pi K L delta T divided by log of 0.24 divided by 0.16. So this content is collected from the textbooks as well as the reference books represented here now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.